Welcome to module 21 of object oriented analysis and design. In the last couple of modules, we have discussed and actually worked out an exercise with our leave management system to illustrate how different linguistic and important analysis techniques can be engaged to extract the classes, the key abstractions, their relationships and so on. In this context, we can go further, and that is our endeavor to do so. But before we proceed further on extracting more and more system information from the specification and start modeling them for proper design, we need a vehicle to express the information that we are extracting. Naturally, our starting point has been certain English documents, interaction videos, and it could be other supporting documents, images, charts and so on. But as we extract the information and start creating the analytical design of the system, we need a language which can be used very compact way and very concretely to express all the information that we are extracting. UML or unified modeling language is such a vehicle. So, in the module today and in several modules that are to follow this and in the next couple of weeks, we will take a deep look into what is UML, how UML is represented, and as we work through different representations of system concepts, designs, parameters into the UML, we will illustrate as an ongoing process as to how we can use the leave management system and create its unified modeling language models. So, with that broad objective, we will start this module by discussing a basic overview of UML. This is what we intend to discuss, and as usual this outline would be available to the left of every slide as we go through the presentation. So, the first question certainly is why do we need something like UML? As we have seen that so far there are two kinds of descriptors that we have for a complex system. On one side, on one extreme is a descriptor which specifies the requirements of the system, specifies different behavior and entities of the system, and typically as we have observed, it is written in a natural language. And as we have repeatedly explained, there could be supporting information, discussions, notes, images and all that. The key difficulty in this form of representation of a system is natural language is often ambiguous, vague, imprecise. From the same text, what I understand, what you understand and what someone else will understand would vary widely. The diagrams help, and yet they could be drawn with different conventions, with different practices. So, this way of representing a system is not a unique clear method by which we can unambiguously precisely understand what the system is all about. The other extreme of representing a system is its implementation. When the system gets implemented in terms of possibly a object oriented programming language. So, if we intend to use C++ or Java or some such, Then we will have the whole system again described, represented in terms of a set of classes, methods, exception conditions, dependencies, modules of subsystems, messages, threads, and so on so forth. Again another description which is very specific and would vary across different platforms, different languages, different paradigms, and so on. Now, our intention, our requirement in the whole process of OOAD is to start with the requirement specification of a system and reach the implementation, software implementation of the system. Both of them we find are difficult, complex to handle. They are not very clear, precise in the expression. So, that brings in the context of using something like a UML or unified modeling language, which is basically a notation for system analysis and design. The first importance of why should you use UML? It is a standard. It is an international standard maintained by the Object Modeling Group or OMG. So, it helps the designer, developer, even the user to capture various artifacts of software design, various nuances, details of software design can be uniquely captured in UML without any scope for imprecision, vagueness, ambiguity, or the viewer or reader dependent understanding. So, it eliminates the issues of consistencies and accuracy that typically will exist in a software analysis and design problem. It minimizes vagueness and imprecision, as I have mentioned, and coupled with all this, it facilitates a robust communication within teams, robust communication between the vendor and the client, and so on. So, the basic process would be that the initial stages of our design and analysis, we will try to interpret the specification from different multiple natural language and multimedia sources and create these UML diagrams, which will be the unique representation and kind of the golden on which the whole system will then be built up. So, what is UML? UML has can be looked at in various dimensions. First of all, it is an expressive modeling language. It is a language to model. It is said to be an expressive language because it allows you to model almost anything that you need to model, starting from specification to construction to visualization to documentation, everything that you need in the whole life cycle of a software development, system implementation development can be captured in UML. For the need of clarity, expressiveness, and precision, UML is almost totally designed as a graphical language. So, it is not which depends either on the vague semantics of natural language, nor does it deal with the complex logic and analysis of the programming languages. It is a graphical pictorial kind of language, and it allows us to use a whole lot of ready to use core concepts. You would recall from the earlier discussions that we had talked about reuse, we had talked about common patterns that occur frequently in complex systems, that occur across domains and so on. So, what UML has done? UML has tried to create semantic expressions for those concepts and made them available as a core in the language itself. So, that very often once you come across such a concept in the system you are going to represent, you would simply be able to find a primitive, find a feature in UML which directly represents that. Besides that, UML provides a formal basis. Maybe for some of you it may be difficult to understand what a formal basis means. What it means is, this, though it is a graphical language, it should not be just taken as a pictorial representation. It has certain strong mathematical foundation which can be proved to always provide consistent correct description of the system alone. And in that process it uses certain meta models, it uses semantics, which is the part of the official UML standard documentation. In addition, in the supportive side, it supports high level development concepts. We will often find UML talking about terms and items which can be directly represented and immediately implemented in standard OOP language like C++. Some of those UML concepts, supported concepts, will actually have even standard library implementation in some of the common OOP languages. So, it is these kind of collaborations, patterns, these are some of the terms that I have mentioned here, patterns, components would be very convenient to represent in UML. Last but not the least is UML inculcates a set of best practices. If you refer back to the very first module where we started discussing as to what are the challenges of constructing a software, we address that there are different issues and maturity issues and so on, for which we still say that the software is developed, but all other kinds of engineering development is actually called construction, where there is a guarantee of success. We had mentioned that all these other fields of engineering succeed so well, are so reliable these days, because over years and years of practice we have been able to develop a set of norms, set of industry standards and best practices, which every civil engineering design or a mechanical machine design has to follow. Similar practices still do not exist that much in software. So, UML can be used as a vehicle to encode these best practices, because UML is giving us a platform in which I can express a concept in a platform independent, language independent, even at times domain independent manner. So, this is the basic essence of UML, and while we discuss this, it is also important to understand and highlight that UML is characterized by openness. What does that mean? That UML does not say that you have to use a specific modeling tool or you have to use a specific language. It does not, it would not say that you must use C++ or you must use Java or you must use Python. It will not tell you that this is a, you should use a waterfall process of development or agile process of development, or you should do test driven development. It will not make any prescription. It is not meant for prescribing any of these or any of the other actual detailed practices that are involved. It is open so that irrespective of what process you follow, what modeling language, what programming language, what platform, which hardware you are planning to use, irrespective of all these parameters, UML would be equally useful for you to model the system and to take it through the life cycle of development. So, a quick bit in terms of how UML got formed. I really do not have the time to go over the detailed history, but that history is indeed very interesting. The concept of being able to model system in a formal way started quite long back, and in 80s we saw a lot of activities, and which went into at least the first part of the 90s, and it saw a proliferation of several different ways, several different languages and protocols to model systems, till majority of the proponents of various models, Buch, Ramberg, Jacobson and so on, you are already familiar with Buch's name. We are following his book very thoroughly. They all collaborated, joined hands, and UML was formally that way created with the formation of the object management group. There is a website on OMG. I would suggest everybody that you go to OMG site, and you will find a whole lot of very useful information, not only on UML, but in general on object oriented analysis and design, and especially you will find information which is oriented towards the current practices. So, in this background, it is kind of the late 90s that UML started existing in its current flavor. So, this is kind of the era of fragmented development. Then people as joined hands, and they put all these together, and the U in UML, that is unified in UML, is actually the unification of all these methods. Some people tend to think that it is called unified because it can be used over multiple phases of SDLC, or can be used to express variety of concepts. Those are also true, but it primarily got its name by the unification of methodologies that it represented in the late 90s. And then over this whole lot of around 25 odd years or nearly 30 years, I am sorry, it was nearly 20 years. It has developed, and OMG manages and versions UML from one to the other, and this UML 2.5 is the current version that is existing in the standard. So, while we discuss UML, we will discuss some of the starting from the early concepts. So, not we will often restrict ourselves to the 1.x kind of standard, because 2.5 has lot of advanced concepts which we may not have time for, but we will take glimpses of 2.5 from time to time as it need. Now, as I said, UML is graphical. So, what it has, the core of UML is collection of diagrams. So, it consists of various diagrams that capture various aspects of software design. So, the idea is simple, that a software system or a system in general, we have seen there are several different complexities, and there are several different ways that we can look at the system. We have discussed these things at length in the earlier modules. So, the UML takes a very simple approach to address this, that it has identified what are the major aspects that you need to know, that you need to decide on for a complex system, and for each one of them there is a category of diagram, and that diagram has specific primitives which help you actually capture as well as analyze the aspects of that. So, for example, you will have a bunch of class diagrams. Naturally, we have already seen that it is not easy to capture all classes into one set. So, a system will have multiple classes, multiple kinds of relationships. So, the class diagram can be built up over this collection into a smaller to bigger set to give you a very unique UML description. And it has UML supports a strongly supports a name unification, which means that across different diagrams and across different modules of the design, the same name can be used, and therefore, we will see that a name that is used in use case to represent a use case will be used in the class diagram to represent a method, the corresponding method. An actor in a use case will become a class in the class diagram representing a particular group of individuals who is taking that action. So, that is a broad basic point, and based on that, this is just to give you an overview glimpse of the whole thing. So, you can see that at the root is the UML 2.5 diagrams, the collection of all diagrams, and then you have two types of diagrams, the structure diagram and the behavior diagram. And as you must have noticed by now, is whenever we draw this kind of an arrow, let me draw it clearly again, that is an open triangle with this, then it means a is a or generalization specialization relationship. So, to describe the UML diagrams, we are taking care of the same notation. This notation is a part of UML class diagram and some of the other UML diagrams. So, we say structure diagram is a UML 2.5 diagram, this arrow, the behavior diagram is a UML 2.5 diagram, this arrow, and so on. So, basically here in this slide you not only see a collection of this diagram, but you see kind of their specialization generalization hierarchy. So, we know that these are the two basic types of diagrams, and then we have a variety of different class structured diagrams like this. There are a variety of different behavioral diagrams like this, and so on. In reading this chart, you have to remember a basic color code. The diagrams that are written in black are part of the standard. So, class diagram or use case diagram are part of the UML 2.5 standard, but the diagrams that are written in blue are at the level of proposals. They are being discussed and they have not yet made to the standard. Some of them may become a part of the standard UML in future, some of them may get dropped also, and there are several interrelationship between them. For example, if you are talking about a composite structure diagram, then you are saying that there are two specific subtypes of it in terms of the internal structure and the collaboration use diagram. So, these are at the level of proposal. So, what we will do this, I am presenting you the whole picture to just give you the current truth of what the UML 2.5 looks like, but we will concentrate primarily on the diagrams in the standard, and there too we will just take up a subset, because it may be otherwise quite a lot of time taking to complete all of the diagrams. We will just take the major ones and discuss those. So, first let me say a few words about the basic two subclasses of the UML diagrams. One is called the structural diagrams, and the structural diagrams show the static structure of the system. So, we have been seeing this notion of static and dynamic description all through. I mean, I would refer you back to our discussions on objects and their nature. We observed that objects have an identity, but besides that they have attributes and they have properties. Attributes are the static struct and properties are the dynamic behavior. So, similarly the diagrams here are also in a way static. Structural diagrams give us the static structure, that is how different parts of the abstraction at different implementation level are related to each other. But this is static, which means that when the system is actually built up, deployed and works, these are not going to change over time. These remain kind of fixed. The other side is the behavioral diagram, which talks about the dynamic behavior, that is how does the different objects, the behavior of different objects change with time. What happens if I want to get into a system and I want to perform a login, I have to perform a sign in kind of activity, then what are the different actions that need to happen in what sequence, in what temporal order, with what dependencies to allow or disallow me to sign into the system is a part of the behavioral or the dynamic behavior. So, if we can note that some of the a subset of the diagrams will talk about structural properties and subset will talk about behavioral properties. So, let us start, just take a very quick look in terms of these. So, the way I have organized is for all the diagrams that exist in the standard, we will first talk about the behavioral diagrams and then we will talk about the structural diagrams. Here I am just trying to make a very brief overview to you about this each and every diagram. We will take up many of them at length and we will have separate modules discussing them, or at times multiple modules discussing them, how to use that, and wherever applicable we will take the case of the leave management system and illustrate how the corresponding diagrams can be met up. So, the most important possibly to start with, and the first fundamental diagram that UML behavioral has to start is use case diagram, where you represent the requirements of a system including the internal and external influences, what is happening around the system, that very gross way. Then activity diagram talks about what are the different activities that internally happens in the system, what are the operations of the system. State chart diagram basically borrows its name from the state transition machine or finite state automaton or finite state machine. So, it means that I can think of that in the system there are several situations where there are a finite set of possibilities and the system keeps on moving from one possibility to the other, and that is what we say is the finite state machine. State chart basically is an enhancement of the finite state machine, which along with telling me what are the different states that a system can be in. For example, in a sign on system I may have signed up, I may not have signed up. If I have signed up, then I may have signed in, or I have not signed in. If I have signed in, then I may have a state of coming in next time without having to sign in again, and so on. So, these are the different states, and state chart allows me to play around with these different state information. The next set of behavioral diagrams are all clubbed into one subcategory known as interaction diagram, because they define different kinds of interaction behavior. Of that, the sequence diagram is most frequently used, which will tell you what is the order of events that happen. The communication diagram will tell us that what is the order in which objects exchange messages. I would just again remind you that our vehicle finally is a client server model. So, when you do all this modeling, finally we would like to take it to some messages being sent from one object to the other. So, the sequence diagram tell us the temporal order in which the messages are sent, and the communication diagram tell us the spatial order or the object to object order of how messages are sent. Timing diagram, as the name suggests, is closely related to the timing information, and interaction overview diagram basically tries to model that how interaction flow be from various sequences, collaborations and activity flows. So, it is kind of sits little bit at a higher level compared to the sequence, communication and timing diagram, which are particularly object based. Interaction overview diagram is often at a level of modules. Coming to the structural diagrams, the main structural diagram of course, are the class diagrams and object diagrams. Class diagrams, and as we go into detailing them after a couple of modules, you will find that you have already come across much of the notation or the diagram conventions of class diagrams and objects in terms of our process of identifying classes and identifying objects. Certainly, the other structural diagram is a package, which basically encapsulates different components and puts them as a part of a bigger module. Further structural diagrams include composite structure diagram, which gives a complete structural view of the system with all its subparts and interfaces and so on. And the complementary to that is a component diagram, which primarily show you what are the physical aspects of the system. So, the composite structure, if it talks about various interfacing relationship between components, the component diagram specifically talked about what components and what static implementation view of these components that you need to describe. And though we are talking about analysis and design, we will find that several of these diagrams actually go beyond that boundary, and deployment diagram is a direct example of that, where you not only just talk about the early phase design, but you talk about the late phase implementation, where you decide okay, if finally this system will be deployed over 5 servers and it has 17 modules, you actually decide which module will run in what server, whether some module will run in multiple servers, whether one module one server would accommodate multiple modules and so on. That whole description of hardware component and software component mapping is given in terms of the deployment diagram. Finally, profile diagram is an auxiliary one, which talks about what kind of profile. For example, if you are implementing on Java, what kind of would you like to use J2EE or you will be using J2ME. If you are using J2ME, would you use an Android profile or you will use an iOS profile. So, these kind of information are often shared in terms of the profile diagram. So, to summarize, we have understood that UML is required to create a standard notation for designing and modeling software systems to liberate ourselves from the vagueness and imprecision of natural language, and also not to get trapped in the intricate analytical and expressive power of the programming languages. UML majorly contains two types of diagrams, structural and behavioral diagrams, and we have seen variety of structural and behavioral diagram overview, and the overall system will be captured in terms of all these different diagrams. So, with this overview, we will in the next module we will take a brief look into the basic design process, design and implementation process of the software, to realize how we can start using these diagrams, and then we will move into the discussions on specific diagrams.